for having me, everybody. It's great to be here. So I've been to many different places in England, but I've never actually been to Northumberland. So it's my first time, and I've been here for a couple of days now and had a chance to check out the locals, check out the local wildlife and some of the local terrains. I've somewhat incorporated that in my presentation. But the topic of my presentation is the future of Mars exploration. So my background, as Herb said, is I'm an aerospace engineer, and I had an opportunity a few years back to work on the Mars Science Laboratory Curiosity mission, which was NASA's largest robotic explorer sent to the surface of Mars. And that was sort of an opportunity of a lifetime from an engineering perspective. So I'll talk a little bit about sort of what Curiosity accomplished, but I'll focus more on what is the future, which is the future of Mars exploration. But as this conference is about sort of expanding your horizons, Herb wanted me to talk a little bit about me, just sort of my journey. So I won't be giving you information on how to improve your business, but maybe more information about how my journey to accomplish what I've accomplished today, and maybe how you can take some of those aspects into what you do. And so the first thing I would say is that you have to follow your passion. And so when I was in university, it was actually a really rough time for the aerospace industry. And I had many people tell me, do not get a degree in aerospace, it's a mistake, you won't be able to get a job, but it's something I always wanted to do because, to be honest with you, the reason why I became an engineer is because I was a huge fan of Doctor Who. So I used to watch Tom Baker and Peter Davidson reruns on the local television network in New York. And I was so fascinated by the concept of this alien that traveled in time and explored alien worlds that I knew as a small child that I wanted to be somehow involved in the space program. I just didn't know if I wanted to be an astronomer, an astrophysicist, or an aerospace engineer. I ended up choosing engineering because I liked working with my hands and developing new technologies. And that's the difference between science and engineering. Engineering is applied science, basically creating new technologies, whether it's for space travel, for telecommunications, or for biomedical imaging equipment purposes. So my family moved to the US when I was 3. So I still have my UK passport. And I was born in Scotland, so hopefully that will help me on the visa front as things move forward with Brexit. So I always knew I wanted to be an engineer, so I got my BS, my MS, and my PhD in aerospace engineering. I've spent the past 15 years working as a rocket scientist, as my PhD is actually in propulsion systems, which means I actually am a rocket scientist in terms of my area of expertise. But one of the other things that I got a piece of advice when I was starting out was that it's good to have more than one area of expertise. So my expertise is in plasma physics, electric propulsion, plasma propulsion systems. You can explore deep space very efficiently. But then I had an opportunity about 5 years into that to work on Mars missions, specifically how to design systems to land on the surface of other planets, with atmospheres and without atmospheres. And so even though it was a departure from what I had done before, I took that challenge because it allowed me to develop a new opportunity. So I spent 5 years working on the development of Mars entry, descent, and landing missions, specifically for the Curiosity mission. Then I had the opportunity to work on developing a system that would land on the surface of Venus. So once again, another slight offshoot of expertise. And then most recently, I've spent the past 5 years developing a quantum mechanics or quantum physics, atomic physics facility for the International Space Station. So what that means is that in life, you're going to have different sort of opportunities that make themselves available to you, and it's important to take them, even though it may not seem like the easiest thing or the best thing, because it will grow who you are as a person, it will grow your area of expertise, whatever that is, perhaps just in more discipline areas within your own specialty, or perhaps completely different areas which will allow you to enter different industries. And the other thing that I would say is that most engineers are actually introverts. I'm definitely an introvert, and so one of the things I was most afraid of is public speaking. And so what I decided to do as much public speaking as I possibly could to kind of get over that hurdle, expand myself. Another thing I always wanted to do, but I was a little bit nervous about, I always wanted to be a pilot. So once again, you gotta sort of push the boundaries, make yourself feel more comfortable. So I went and got my pilot's license. I've been doing that for about 10 years now. And then same thing, I always loved motorcycles, but I was a little bit nervous about getting on a motorcycle. So I took a training class, got certified, and I've been riding motorcycles for the past, I guess, probably about 12 years now or so. So I think the message there is that you always have to expand your horizons. You have to push yourself beyond what you think you can do to the things that you want to do. And you'll get there as long as you're able to challenge yourself and sort of develop those new skills. And so what that really means on the sort of commercial front or the career front is recognizing opportunities. So the only reason why I went into plasma physics, plasma propulsion systems, is because I had a professor at my university who said, do you want to come and work at JPL to work on sort of testing out the next engine for a mission that was already in space, going to a comet and asteroid, and then developing that engine to go to a different asteroid, which is basically Vesta and Ceres. And so that was my first opportunity to work at NASA, so obviously I took it, and I developed my expertise. I got my PhD in it whilst working. Then once again, I went to Mars. My specialty on the Mars mission, Curiosity, was the supersonic parachute. So I have an entire talk I do about that, which I won't do today because I only have 20 minutes. And then the other point about recognizing opportunity is that I was on my flight out here from LA, and I'm in the Boeing 787 Dreamliner, amazing plane. So I'm like, I should just ask the stewardess, can I go to the cockpit? So I'm like, I'm a pilot, and I really want to sit in the cockpit and see what it's like. And they're like, of course you can. So then I went up and talked to the pilot crew in the front. They let me sit in the seat, and I was completely nerding out. But it was a lot of fun. So the point is that you have to ask questions. You have to challenge yourself. You have to look at every opportunity that presents itself and take it, because you don't know where it's going to lead. It's a little bit different from risk in terms of financial risk that some of the other speakers have talked about, but it's maybe a little bit of risk to yourself because you're taking yourself out of your comfort zone. But next I want to talk about how do we land on Mars. So enjoy.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun, 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
A parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it will only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms, and it could damage instruments. So the way we solve that problem is by using the sky crane removal.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage away to a safe distance from the rover.
What's really awesome about that is it looks like science fiction, right? But it's actually science fact. So we successfully accomplished that 5 years ago, and I think we like to say it's probably one of the greatest engineering feats of the past 10 to 15 years. And so even though it's not people on Mars, it's a robotic geologist on Mars. And when you send something that you built and designed yourself, it's almost like being on Mars yourself. So that was pretty exciting. So first of all, though, why are we so interested in Mars exploration? And there's two key reasons. One, you can kind of see here, I'll talk you through it. The planet on the left is Venus, in the middle is Earth, and the planet on the right is Mars. And these are all called the terrestrial planets. And what we know is that at the beginning of the formation of the solar system, all three planets are actually relatively similar in terms of having water on the surface and in terms of having a thick atmosphere. However, now Venus, which is one planet in from us, now has a surface temperature of 475 degrees C and a surface pressure 100 times where Earth's surface pressure is. So it's basically like a hell, the best way to describe it. Earth, of course, is nice. You know, we live here pretty comfortable, lots of water, lots of oxygen to breathe. Mars, on the other hand, is actually the exact opposite. It actually gets quite cold, you know, up roughly minus 120 degrees Fahrenheit. The surface density is only about 1% of what it is on Earth. And the temperatures are pretty low, and the radiation environment is pretty bad. So what happened to these planets to make them evolve in this way? And one of the ways that we answer this question is by sending spacecraft, both to orbit those planets, as well as rovers and landers to stand on the surface of the planet. And the reason why that's important is because everyone who's done any kind of math knows that you need 3 data points to make a line, right? Or you need 3 data points to get a trend. How is it that Venus went the way it is? How is it that Mars went the way it is? So we can actually answer questions about our own future by understanding how the terrestrial planets evolved. Now, of course, the other reason is that at some point, human beings are going to want to live somewhere besides Earth. And it turns out that Mars is actually a pretty good destination, both because of its proximity to Earth and because it does have resources on the surface that we can utilize to set up future human colonies. Anyone here a fan of the show The Expanse in the room? It hasn't quite yet filtered over to the UK, but it's actually a very good show, and it's about how human beings now live on Mars, and they haven't yet terraformed it, and they also live in the main asteroid belt. But it's a nice sort of vision of the future of what happens when, you know, too many human beings on Earth have to expand to other planets. So the two reasons are to understand how the planets evolved, and can we, in the future, send people there. But what's so interesting about Mars, though, in particular, is that the image on the top is Olympus Mons. It's basically the largest volcano in the solar system. It's about 3 times the height of Mount Everest. But now, all the volcanic activity has appeared to stop. Why did that happen? We don't actually know. Similarly, another feature on Mars is Valles Marineris, which is sort of Mars's version of the Grand Canyon. So some of you have probably been to the Grand Canyon on vacation. However, it's about 6 times as deep as the Grand Canyon is. So Mars, even though it's a small planet, has these amazing surface features because it had a very active geological past. But something happened to make it stop. We don't actually know, but we do have hypotheses. And one of those hypotheses is related to the fact the magnetic field is now essentially gone, which means at some point it probably had a molten, rotating core which created that magnetic field. It was disrupted perhaps by some kind of asteroid impact. We don't actually know. But once again, with the scientific method, the way that you determine the things that happens is you have a hypothesis, and you go send a spacecraft to make a measurement, which then tests that hypothesis to determine what happened. But of course, the impact there, of course, is that if we had some kind of impact like that, it would affect our magnetic field. The impact there is that you'll lose your atmosphere, then you'll lose your water, and then game over, right? So it's important to understand how the planets evolved. So by a show of hands, who thinks that we have actually found water on the surface of Mars today? We actually have. We found it in the form of frozen water, and we've also found it in the form of sort of a wet mud. And so the picture that you see on the lower left here is those black streaks is actually what we believe to be wet mud flowing down the sides of cliff faces on Mars because there's water frozen in the subsurface. And because Mars is rotating on its axis as it goes around its orbit around the sun, the planet heats up and it cools down. And when it heats up, some of that liquid actually comes out. And this is a discovery that we made with a spacecraft which we've had orbiting the planet for over 10 years now. So we have incredible high-resolution images of the surface down to the point where we can look at the size of sort of rocks on the surface. So we do know there's no alien civilizations living there right now. But it is pretty exciting that we figured that out. So why is water important? Well, the obvious reason is that if there's future human colonies, we can make use of that. And of course, you know, you want to make beer when you're on the surface of Mars. So yes, one thing I'd say, I'm a beer snob, but I have found good craft beers in the area so far. So who by a show of hand thinks that there's moons on the surface of Mars? Sorry, moons orbiting Mars versus none? So there are actually two. There's Phobos and Deimos. And so they look really odd because they're actually pretty small, which means that they haven't compressed into a spherical shape under their own gravitational pull. But the reason why this is important is that we could actually set up communication centers on the surface of these moons instead of going all the way down to the surface, right? Because in order to have a nice network of something like a GPS, you could actually utilize these natural satellites to put telecommunication stations on so that we can have an easy communication from the surface to orbit back to Earth. And then what people also may not know is that these asteroids actually contain minerals, and they also contain water. So you could actually use these as sort of depots for resources for deeper space missions as we go further out into the solar system. So there's a whole bunch of really neat architectures which are in the future for hopefully, you know, expanded human colonization of the solar system. And so now we come back to technology. So in order for us to be able to learn more about the surface of Mars, we've used robotic explorers. And these are basically robotic platforms which use intelligent systems to be able to make measurements for us and send the data back for us to analyze. And so what we've seen over the course of the past 20 years or so is the evolution in this technology. And that evolution has been somewhat changed by us learning how to do it better and better, and because we have advances in technology each time, whether it's from a power system perspective, or from a battery technology perspective, or from a computational power perspective. So the very first rover that we sent was about the size of a Tonka truck, which is, you know, so big. Then the next rover that we sent, so the first one was in the basically late 1990s. The early 2000s we sent the Mars exploration rovers, which were basically the size of a lawnmower. And then the most recent one that we sent, which is Curiosity, is about the size of a small car. And for reference, I did some recon here. So we're looking at sort of like an adult sheep-sized rover for the Curiosity rover and a little baby sheep for the tiny little Sojourner rover. And the reason for that is because if you want to carry more scientific equipment, you need a larger wheelbase. And so the Curiosity rover has a larger wheelbase, so we can carry more science equipment, make more interesting measurements. And so all of that evolution in technology over the course of the past 20 years has enabled us to create a greater data set to help us understand how Mars evolved and to make measurements that will facilitate the next generation of missions that hopefully will include people in the next 10 to 50 years or so. So one of the important advances that we made from an entry, descent, and landing perspective is landing accuracy. So what this chart is here is sort of like a bullseye, a dart board on Mars. And so back in the 1970s, we actually sent the Viking rover, and our landing accuracy was basically, just for reference, the distance between Newcastle and Liverpool, you know, roughly 175 miles. And so we didn't know where we were going to land, except that it was going to be in some space with an ellipse, a diameter of 175 miles. So if you wanted to land in a place much closer, so for example, the distance between Newcastle and Blythe is about 12 miles or about like 18 kilometers or so, then you would have to have more precision in how you land. You think about it, you're going, you know, 400 million miles away trying to land in an accuracy the size of a distance of around 20 kilometers. And so over the course of the past 30 years, we've improved our landing accuracy with a whole nother suite of technologies. And so this, I'll give you an example as well, is the length of Hadrian's Wall. So back in the day, in the 1970s, we didn't know where we were going to land on Hadrian's Wall. In order for us to send people to Mars, we will have to land at a particular location, a particular fort outpost on Hadrian's Wall with that level of accuracy. We're not there yet, but we've gotten down to basically the size of around 20-kilometer landing ellipse. And so this shows you the example of where it was that we landed on Mars. We landed at a place called Gale Crater. And the challenge here was that in the middle of Gale Crater was a large mountain, about 6-kilometer high mountain. And the sides of Gale Crater are crater walls. So you have to have a landing accuracy so that you land not smacking into the mountain in the middle, not smacking into the crater wall on the side. And so we did that by essentially creating an entry vehicle which was an airplane. Even though it doesn't look like an airplane, it's an airplane because it has a lift-to-drag ratio. And so this, this basically is just showing you once again, the landing ellipse size that we work to is basically the distance between here to Blythe. Can someone open this video or? So this actually gives you the concept of how we actually land. We use the concept of aerodynamic drag to slow down. We use the atmosphere to slow ourselves down. We go from hypersonic speeds to supersonic speeds. We then deploy a very large parachute, probably about 3 times the size of this room, which then slows us down even more, roughly from around 1,000 miles an hour to 250 miles an hour. Then we reach terminal velocity. We can't go any slower. So at that point, we actually cut off the parachute, and we do the rest of the descent, the rest of the slowing down on retro rockets towards the ground. And so this takes us down from around 250 miles an hour down to around 50 miles an hour or so. And at that point, we start to use the sky crane, which is basically the rover is sitting underneath this little spacecraft, and it's lowered on a set of 3 tethers, which are basically from the height of this room down to the surface. The wheels touch the ground. We cut those tethers. That little spacecraft on top, or big spacecraft on top, actually flies away, and now we've landed on the surface of Mars. So this is a very different architecture than the architectures that we used before, and the reason for that is because we wanted our landing platform to be our actual rover, because it gives us more mass, and it also gives us a much more precise landing capability. So this is an example of what we developed by learning from each prior mission to facilitate a much larger payload on the surface of Mars and a much more precise landing location. And we basically were able to select a location which we believe to be an ancient body of water, which it has turned out to be. Of course, now it's dried up, but we have evidence on the surface that that's the case. So this is a very complex engineering system. That entire sequence is done autonomously. There is no human being in the loop, flying that because of the time delay between Earth and Mars. And so all of that is done from basically guidance, navigation, and control, software in the loop, with the sensors on board telling you basically what your speed is and what your altitude is, and then controlling the thrusters or controlling the different timing sequences to get you to that level of precision. So that was the engineering challenge associated with landing something the size of a small car on the surface of the planet. So what is the future? So one of the biggest challenges for space exploration is power that's available to you. And so as you get further away from the sun, you actually get less radiation from the sun, so you generate less power for the same solar array area, which means that perhaps you can have really large solar farms on Mars, or perhaps you have to come up with more advanced power systems. So we actually used a more advanced power system for this rover, and something like this would need to be developed even larger, even more efficient for future human missions to the surface. So this is a whole area which has to be developed and is ripe for development over the course of the next 10 to 15 years to be able to have more power on the surface. But just for reference, this system only generates roughly around 100 to 150 watts, right? That's not a lot of power, right? So if you had an entire human colony, imagine how much power you'd have to generate. You obviously have to generate kilowatts. So you need much more efficient power systems to facilitate those types of architectures in the future. So another interesting aside that I like to talk about to people is that where we go on Mars looks eerily like Earth. So this is the landing site where Curiosity landed. However, if you've ever been to the desert in the United States, it actually looks really similar. And so even though the atmosphere is very thin, it's primarily CO2, it isn't going to be that different from us to be able to become used to it. I'm probably running out of time, so I'll go a little bit through this. So for autonomous systems perspective, the rover actually drives itself. It uses the computer on board. It has images where it's collecting them, doing image processing in the loop so that it avoids any hazards. So from a distance, we tell it twice a day basically what to do for the day. It goes off and does that using its own autonomous systems to keep itself safe. Also, what's in the future? So I thought you were taking a selfie before, but you won't. But what the rover actually does is it does take a selfie of itself. And the way it does it is it actually has cameras on the end of its arm, so it's able to piece together a 360-degree view, which allows us to actually take really awesome pictures, right? But it also allows us to monitor the health of the rover from a visual perspective. What is the challenge for the future to send people there is basically to put more mass on the surface, larger payloads to the surface. And so that means more efficient propulsion systems, more efficient decelerator technologies like I showed you before, and by larger payloads, hope this doesn't offend anybody, basically larger people. I was looking around for all kinds of Newcastle stuff this morning, but basically people are very large, right? And so you need to be able to send more mass to the surface to be able to facilitate those missions. So what is also in the future? Environmental control systems. We will have to live in pressurized environments. We'll have to have our own air to be able to survive on the surface of Mars, in addition to protect ourselves from the radiation. So this is also something which is ripe. And I was talking to a gentleman last night at dinner whose company is actually working on sensors that monitor what the environmental quality is on board the International Space Station. Once again, ripe opportunity. Surface mobility. You wouldn't want to stay in the same location, right? So you're going to have to develop pressurized vehicles to drive you different points on the surface. You can collect samples and perhaps visit other colonies as they're built up on the surface of Mars. Now the big challenge, which I really like, is about being green on Mars. So in situ resource utilization. You would like to use the environment to create power. You can do this with a combination of solar array technologies. You want to be able to protect yourself from radiation, which is a little bit harsh on the surface of Mars. You can do that actually by building your habitats underground, using the soil to attenuate some of that radiation. If we can tap into the subsurface reservoirs on Mars, we can get water to wash ourselves, grow plants, actually split up the H2O to create O2. And then could we potentially make fuel? We actually think we can. We think we can make methane. And can we also grow plants which don't need that much oxygen but can primarily survive off of CO2? And so what that means is that if you're living on Mars in the future, you will have to be a vegetarian. So for the people from Greg's here, who I was talking with last night at dinner, there won't be any meat on Mars. You're all going to be eating vegetables, unless, of course, you can make some kind of meat substitutes. That's your challenge appropriate for you in the future. But it's really neat, though, because you have to become sustainable, self-sufficient, green, in order for people to be able to live on the surface of another world. And then to wrap it up, basically, future exploration of Mars is going to take a whole variety of expertise. It's not just engineers, right? It's going to take engineers, it's going to take artists, it's going to take musicians, it's going to take people who can basically establish a new society on another planet, many, many millions of miles away from Earth. And so if you have any questions, you can either talk to me at dinner, or you can send me a tweet, or you can send me a message on Facebook. So thank you.